So anyway, the main reactions of double bonds are known as addition reactions. You add something to the molecule, and what you add is shown here very roughly. Here's this double bond in which the carbon, each carbon that wants to form 4 bonds, well, it's got 2 bonds to other things, but then 2 bonds wasted between these 2 carbons. It would actually be a much happier carbon atom, believe it or not, most of the time, if instead of this carbon having double bonded to this other carbon, it's got a single bond to that carbon and another bond to something else. Same for this carbon, it would rather just have a single bond to this one and a bond to something else. So most common reactions of these double bonds is where you add something, in this case depicted as XY, across the double bond. So we take our XY, we add it to the double bond, the X goes onto one of the carbons, the Y goes onto the other one, because we've broken one of the bonds in the double bond. 2 addition reactions we're going to look at more closely are as follows. One of them in which you react an alkene with HBr, and the H goes onto one carbon, the Br goes onto the other carbon as shown here. And then we'll also look at the same type of reaction, again an addition reaction, in which we add Br2 to this, and so one of the bromines goes on one of the carbons, one of the bromines goes on the other carbon. Believe it or not, these 2 rather simple looking reactions can get really rather complicated when we start thinking about it and following it properly. Let's start by considering propene. Make sure you can see it's a propene because it's 1, 2, 3, so it's prop, it's got a double bond, so it's ene. Now what I need you to notice about this is that this is an asymmetric alkene. On one carbon we got this CH3 group, on the other carbon we don't have the CH3 group. So there is a difference between this carbon and this carbon. We say this carbon is more substituted because it doesn't have all hydrogens, it's got one non-hydrogen species on it. If there was a second one on there, we'd say it was disubstituted. But anyway, this carbon more substituted than this carbon. So when we add HBr to this, well, the H is going to go on one of the carbons and the Br is going to go on the other carbon of the double bond. But because these 2 carbons are not the same, we could have this situation in which the hydrogen goes on to the more substituted and the bromine on the less substituted, or we could have this situation in which the bromine goes on the more substituted. 2 possible products of this reaction. Okay, now what would you get? Would you get a mixture of the 2, do you think, or would you get one specific product? And the answer is that in this particular reaction here, you get one specific product. The bromine is going to go onto the more substituted carbon. It is a so-called regio-specific reaction, right? The reaction is one in which a specific atom goes onto a specific region of the molecule. This is an example of so-called Markovnikov rules. Now this is a Russian chap, Markovnikov, so the way that it's spelled would depend upon really people's preferences. You'll see it called Markovnikov, you'll see it seen Markovnikov. I think Markovnikov rolls off the tongue a little bit better. And Markovnikov said that the more electronegative atom, in this case the bromine, is going to add to the more substituted carbon, in this case this one here. Okay, now can we try and explain why this is? Can we come up with the so-called mechanism of this reaction? And one of the, depending on your preferences, either really fun things or really horrible things about organic chemistry are the mechanisms of the reactions. How do the reactions happen? Well, let's talk about this one, but in doing so, let's flip around this molecule. Instead of looking at it flat on like this, let's turn it around so we're looking at it so that this hydrogen is coming out at us. That's what this wedge means. This hydrogen is coming out at us. That's what that wedge means. And now this CH3 is going away from us, and this carbon is going away from us. So it's kind of like, instead of looking at it down like we're doing here, we're looking at it from this direction in the paper. Hopefully you can see that. Well, if I draw it out a little bit more appropriately size-wise, the blue little balls are hydrogen atoms, and this big red ball is that CH3 group. So you can see the effect of the asymmetry having that CH3 there. You got a big bulky chunk here. This substituted carbon here has got a big chunk. Now imagine the HBr molecule comes up and approaches the molecule of propene. It's not going to come from this direction because there's this big fat methyl group there. So it's going to come from this direction, and I hope you'll appreciate that it's going to come in so that the hydrogen is coming in first. Okay, now this hydrogen here is attracted to a fairly electronegative atom. It doesn't like being attracted to a electronegative atom, and so these carbons say to it, hey, we've got some spare electrons here, why don't you help yourself to 2 of these electrons? And so the hydrogen says, I would far rather be bonded to these carbons than I would be bonded to you, bromine, so why don't you go away? Now, if we're going to break this carbon-carbon bond, and we're going to take 2 of those electrons and make a bond to the hydrogen, which of these carbon atoms will the hydrogen go to? Well, it's going to go to the less substituted one, because that's the one it sees first, right? That's the one that it can get to most easily. The way we depict this is we use what organic chemists call curly arrows. So here the 2 electrons from this bond here are going to go towards the hydrogen, and then the hydrogen is going to say to the bromine, you take your electrons and stick it, and so you end up with this picture here. 2 electrons gone from this carbon-carbon double bond, so now it's just a carbon-carbon single bond. Those 2 electrons have made a bond to this hydrogen here. Okay, now because that hydrogen's there, these 2 hydrogens are going to move away a little bit, so you get a tetrahedral instead of a trigonal planar carbon. This bromine here that was bonded to the hydrogen has taken both the electrons, so now it becomes a bromide. Okay, now of course we've created an anion, so there must be a matching cation. We'll think about this carbon here, the more substituted carbon. It did have a double bond, now it's just got a single bond without anything to make up for that, so it now has a positive charge. So this is called an intermediate because we haven't finished the reaction yet, and it is a carbocation intermediate. It's a cation positive charge with a positive charge on the carbon atom. And as you get more into your organic chemistry, you'll actually see another reason why this is what's made here, and that's because the more substituted carbon is a better carbon to have the carbocation on. But that's a little bit further than we need to go to today. Anyway, so now we got this cationic intermediate, and we got this anionic bromide. What do you think a bromide anion is going to want to do with the cation? Well, it's going to want to sneak in and make a bond with this carbon atom. Okay, now it would probably come in, it could come in from that direction, or it could come in from the bottom. Okay, and so either way, you're going to make a new molecule in which this right-hand carbon, of course, has the hydrogen from the HBr in its original 2 hydrogens. This carbon has the methyl group that it was with them originally, the hydrogen that it was with originally, and then a bromine that's either come on from the bottom or come on from the top. Either way you look at it, we write out its structure, and it's the one that we predicted, the one in which the bromine atom has gone on the more substituted carbon atom. Wasn't that fun? Okay, we've got a regiospecific reaction in which HBr, when you react it with an alkene, adds in a Markovnikov fashion such that the more electronegative atom, bromine, attaches to the more substituted carbon. And we've explained that in terms of so-called steric hindrance because of the effect of this bigger group, and it also has to do with the formation of this carbocation intermediate. One of the things that's fun with organic chemistry generally, is that sometimes you can tweak reactions and you can get completely different results. And so it's fun to take the regiospecificity that we saw with the HBr addition to propene in this example and tweak it a little bit and see if we can mess with that regiospecificity. It's actually not that hard to do. Take the same thing, propene, right, drawing it here flat on and then from the side here. React it with HBr, but now instead of just doing it straight off, let's do it with some peroxide in there. Kept it nice and simple with hydrogen peroxide and some light. What you find if you do this is that the bromine doesn't go onto the more substituted carbon, it goes onto the less substituted carbon. This is a so-called anti-Markovnikov addition, in which the more electronegative atom, bromine, goes on to the less substituted. Now let's see if we can't explain mechanistically where this comes from. Well, We start off with our peroxide here, and again I'm keeping it very simple using hydrogen peroxide, and you have this oxygen-oxygen bond. That's what defines a peroxide, and it's a very weak bond. In fact, if you shine light on it, a lot of times you'll break that bond. You break it so-called homolytically. That means that the two electrons that were in this bond, one goes to one oxygen, one goes to the other oxygen. What we saw, of course, in the previous reaction when we broke the HBr bond was that both electrons in the HBr bond went to the bromine. That was a heterolytic bond cleavage. Anyway, so we homolytically cleave this peroxide bond and we get two substances HO that have this electron here. These are called free radicals. These are really, really reactive because this electron wants to find a buddy to make a bond with. Now, if we take one of these HO radicals and we could bring it close to an HBr atom, what happens is shown by these curly arrows is this. One of the electrons from the HBr bond goes with the hydrogen to make a bond with the HO free radical. The other electron, again homolytic cleavage, goes onto the bromine to make a bromine free radical. In other words, drawing these out with pretty pictures, it's going to look like this. There's the HO bonded to the H, so in this case we've made water, nice and easy, and we've got this bromine free radical here. Very reactive, this lone electron looking for a buddy. Well, where might it find a buddy? Well, in a propene, because that is, of course, what we're reacting. We've got lots of electron density here in this carbon-carbon double bond with 4 electrons. So the bromine radical will come close to the propene and react like this. Now let's take this rather slowly as we look at it. First of all, it's going to come in more likely from this direction than this direction, because again, you've got this big honking methyl group there. One electron goes from the bromine. One electron comes from the carbon-carbon double bond, making an extra bond between the carbon and the bromine. So this are 2 electrons in this bond. One was originally on the bromine, one was in the double bond. That means there's 1 electron left from the double bond that is now isolated on the other carbon, on the more substituted carbon. This free radical again is something like the carbocation. It's better when it is on the more substituted carbon, and of course it's easier for it to be made by the bromine coming into the less substituted carbon. It's again extremely reactive. What could it react with? Well, another HBr, just like this. So another HBr comes up, 1 electron goes from the HBr bond, the electron goes from this, the extra electron goes from this carbon, so you make a carbon to the hydrogen bond right there. 2 electrons, 1 came from the HBr bond, 1 came from the carbon, leaving this bromine behind again with 1 electron. So we've regenerated a bromine free radical that can go and attack another propene molecule just like this one. This is a so-called chain reaction that if you haven't learned about before, you will learn about again at some stage. Okay. Again, the product that we're going to make in this way now, the anti-Markovnikov, in which the bromine, the more electronegative, goes on the less substituted carbon. So that's one type of reaction, one fun reaction associated with these alkenes, this regiospecificity, when you've got what you're adding is different atoms of different electronegativity. Sometimes you go as Markovnikov, so the more electronegative atom goes on the more substituted carbon, but you can tweak things to get the anti-Markovnikov addition so that the more electronegative atom goes on the less substituted carbon. These are examples of regiospecific reactions in which the reaction specifically goes in a particular region.